Okay, welcome everybody on C++ London Uni. My name is Tom. I'm one of the co-hosts. The person just walked out of the room, obviously, is Oliver. He will be leading today's class. And we have another tutor, Tristan. So for those who don't know, we are a non-for-profit organization. We are teaching people for free to become software developer. And we rely on people like you who help us by attending and as well helping to get this project going. So today I get a very nice first announcement. As you can see, I got a fancy new handset which I don't even know how to wear, but that's not important. The important are guys there. And as well we have a lasery thin pointer which will work on the screen and as well on the video. So when anybody's later on watching the videos, finally you will see what actually guys are talking about and pointing to, which is obviously a great help. It will improve the quality of the of the recording. As well, the important part is this thing, as you can see, is wireless. So even if the guys will move further away, you can hear them on the recording, which I suspect will be another benefit to people who learn. So what do we have today? First of all, massive thank you to sponsor. These people here, yes, these people here, if I can make this work, hopefully I won't. Anyway, these people here made possible for us to buy this kit. So thanks to them, the class is improving. Thank you very much, really appreciate it. You're making the difference. As you can see, we have this super amazing gizmo, and when you or other people will rewatch, it will be much nicer. The most important subject of today, we are looking for new home, and I'm really struggling the last few weeks to get places, and I don't know how long we can rely only on Mimecast. So a massive ask for all of you. Can you please reach to your friends, check whether the places or you work for may be able to host us, because relying solely on Oli is really tough job. As you can see, there is lots of running around, even setting up tables, yes, not to mention getting pizzas, print out stuff and so on. It's a massive undertaking for one person. I can't help Oli way more. I would love to, but I can't, because I'm not an employee of Mimecast. I can't go to restricted areas, and all of that is basically on Oli hands, plus obviously running the class. So if you know anybody, it could mean whether we are meeting next week or not. So it is really important. Talk to your friends, and if you know anything, send them through to me. Now, just a reminder, how do we work? Basically, we meet twice a week on Tuesdays and Thursdays. Tuesday, like today, we're running the lecture where we will present some of the new materials. And on the materials, if you log on to our website, you may notice at the bottom part where I publish the details on when the classes are and workshops, we published a list of further modules that we'll be teaching you. So there's lots of exciting stuff there. Go on, have a look. The idea is, as far as I know, subject to change, the next module after this will be core developer tools. So basically we'll teach you about GitHub, CMake, and other stuff, I think Jenkins. And after that, there will be a module which will be about TDD or BDD, so test-driven development or behavior-driven development. So using catch and so on to make sure that your program works properly. On Thursdays, yes, going back to topic, on Thursdays basically we do workshops, so you apply the knowledge which you gain on Tuesdays. After that, what to do? As I said, it's a two-way street. Unfortunately, we're not sponsored by anyone. We're looking actively for sponsorship, but they don't come easy. The big guys don't really want to easily separate from the cash or other goods and help us. So unfortunately, we have to rely as well on you. And there is a couple of ways you can make a difference. If you've enjoy, and this is very important. If you are fully employed, if you earn the salary every month, so consider joining the Patreon. So you can there decide how much you want to, for example, contribute on a regular basis, pretty much every month. So it could be as little as £1, £2, or as much as thousands of pounds. Obviously, we don't expect anybody to pay thousands of pounds, but if you benefit, a couple of pounds definitely makes a difference, because as you can see, we can buy a gizmo which will improve the classes. The second one, obviously, is sponsors. So if you know any company that would be happy to, for example, advertise with us or do something else and help us with paying some of the bills, it would be amazing. Yeah. If we would like to go to the previous place which would be the cost for a room for one lesson, so lesson like today, it's between £400 and £600. So it's quite a lot of money, and you know, in order for us to come back to that nice place, we need to gain pretty much quite a big momentum. So sponsorship might be very, very, very interesting. And finally, or for this slide at least, make sure these guys are fed and hydrated at the end of the session. We're going to pub, after heavy work they putting. It's a good idea to buy them a beer or two and maybe some food so they don't go hungry. Now, there is a very important announcement before I go to the next slide. Oliver just turned 30, so happy birthday! Now he no longer can claim he's young.
Did I ever?
Of course. USB sticks. If you need it for your help, basically, if you have a machine you don't know how to set up, you can purchase one of the USB sticks. It turns into the live operating system, works, and gives you basically the ability to do anything you want on Linux and obviously programming. Social media. How many people use social media? How many people did share or write anything about CPP Londonini?
Who doesn't use social media at all? No one put their hand, so they're lying.
Okay, so those who said they use social media and didn't raise the hand, I did share some stuff. Please do, because you have the followers, friends, or whatever the name is. If you spread the word, more students will join. Then if we go to any sponsor, they will be much more keen if they see, oh, you have so many. Oh, that's better. Yes, that brings us basically, it makes our job easier, and basically secure that we will be going for further. So do write short article about us. Like, look guys, I found this really cool organization called C++ London. They give the free classes. Take a couple of photos from our website, publishing, or click on or share, so more people is aware of us. I don't know, did anybody hear about girls.code? Hands up who did. It's a similar organization, but they concentrate on young girls to bring them into the software development, mostly creating websites and so on. And their goal is, I think, to create 30,000 developers. Yes, we don't have such an ambitious project. Yes, we don't want to go to thousands and thousands, but they do pretty much exactly the same thing as we do, and we try to learn obviously from their experience, and they can achieve. They're getting much further. Yes, we are smart people as well. Yes, fairly smart. Yes, I'm not talking about myself. I'm talking about the others. You are very smart, so do help us and spread the word. And obviously, until we finally settle somewhere in a permanent home, please do check the website to make sure that you'll go to the right address. And I try to keep as many updates on the website as possible on Twitter, Meetup, and so on. So please do check, but the mostly please do check the CPP London Uni. And pretty much that's all from me. I'll be passing as soon as Oli walks back in to the room. I'll be passing the mic and the thingy to him. Just walk in. So I'm passing to the person who will tell you way more interesting stuff. Thank you very much.
Hello, yeah, okay, great. Right, so let's just switch the old slides over. Tom, if you could find an extension cable, that would be great. And so we will start very, very soon. Let's just get up there. Right, here we go. Oh, I forgot to put animations on this. I knew I'd forgotten something. Right, I'm really sorry everyone, but these slides are going to be slightly haphazard. They don't necessarily have to be. Right, 1 second. Let's just fix that one. We can fix this one. There's always something you forget, isn't there? Fix this one. Fix this. Too much organisation, unfortunately. Right. This is good. This needs to be fixed. This needs to be fixed. And this one's fine. Okay, much better. Didn't animate that, so I'll have to go through it manually. That's fine. Okay, right. Hopefully we're ready. So I got all the slides done and then never animated part of them, so that's a shame. Right. Here we go. Okay, excellent. Let's see if the clicker's working. Got our fancy new clicker. Over here. If we do, was it Command L for laser, I think? Yeah, there we go. So you should be able to see a laser pointer now. That's good. Cool. Okay. And then which way does it swing? Is it left to right or right to left? I have no idea which way it's going now. Okay. Right. Okay. So, obligatory, the feedback slide. Yeah, we love having the feedback. We like to hear from you. I hope these new gadgets work out well. I've tested them and they seem to do fine, so the clicker's obviously the best part for me, really. Of course, the microphone should improve the quality of our YouTube videos. And also in larger locations, since it's wireless, we can communicate it across to speakers eventually if people can't hear. Right. So, there's already one I've missed. So last week, the things you went through essentially were several crucial OOP concepts, mostly revision, of course. We didn't cover absolutely everything, so the bits we missed, I'm going to sort of slice and dice into this session. But of course, it was essentially inheritance again. Oh, this actually works. Look at that. Can you see the laser? Does it will show up? Okay, cool. But if I also use this, where's it going? Whoa. There we go. So inheritance, composition, interfaces, enums, and of course the static keyword for sort of shared data and shared functions. But unfortunately there was a couple of pieces we didn't, so we'll go through those. So first we're going to revisit the explicit keyword. Does anyone here remember the explicit keyword? Really? Okay, we got a couple that remember what it does. Okay, excellent. And again, a great quote. If debugging is the process of removing software bugs, then programming must be the process of putting them in. So, the explicit keyword. Obviously, C++ is helpful and very clever, and it wants to make our lives mostly easier, except when it makes our lives harder. But sometimes it's, of course, too clever and ends up making our lives harder when it wanted to make it easier. So, let's have a look at a bit of code. So we have a struct which we're going to call shift data. We then have a constructor. Obviously it's a constructor because it doesn't have a return type and because its name is exactly the same as you know, the name, the type itself, the struct itself. So my laser page itself, you can see this is the name shift data, this is the name of the constructor matching. It takes a const char star. It's not important what it does, so it's just exposition, it's empty. And of course we just close that off because it's there for demonstrating the usefulness of the explicit keyword. We've then got a function called launch the nukes. So, you know, fairly dangerous sounding name. It returns nothing, it's void, takes no arguments of course, and you know, we'll just have it print boom. Okay? So we don't have the power to launch any real nukes just as well. And then we've got a harmless function we're going to call change shifts. So maybe it's managing the guard shifts, so we're guarding the nuclear launch codes. And it just prints change shifts. Harmless. And then we have a third function called doOperation, which takes an instance of shift data, as you can see here, by value, and that calls launch the nukes. Okay. But then we have an overload of the same function, so you'll know that these two functions have the same name. And this one takes a char star, takes a pointer to an array of characters, similar to this or boom, right? They're arrays of characters. And we just call change shifts on the second one. Harmless. Cool. One's dangerous, one's not. We have our main function, the entry point, and we call doOperation and we pass it. Well, as you can see, it's an array of characters, right? So, those of you who've already been here and have seen this session, this bit before, you notice what happens, stay quiet. Whoever hasn't seen this before, what do you think is going to happen? Which overload of doOperation are we going to call? And why? Any answers? Let's take a guess. There's only two possibilities, right? There's only two overloads. So can you see main there? You can see what it's passing. So this is a complete example. It's passing some chars. So is it going to call the doOperation that does launch the nukes, or the one that does change shifts? Anyone? Well, yeah. Unfortunately, it launched the nukes. Does anyone know why it launched the nukes though? Because obviously shift data is its own type, right? Shift data is not actually a char array, it's not a char star. So why did we end up with it calling one that's shift data? Correct, absolutely. So, as Jonathan just pointed out, or stated, this seems safe string right here is a const char star array, which means that because this is a char star, it's not strictly compatible. However, this one does take a shift data, so the compiler will look and say, well, what can we construct a shift data from? Well, as it happens, we can construct it from a const char star, and as a result of that, it will go ahead and do the conversion. This is called an implicit conversion, which obviously makes sense in the context of what we're looking at. So, as I've just said, we know why it's happened. We can fix this. Even though what we didn't want to happen has happened, this keyword lets us fix it. So, ta-da! We stick the word explicit in front of it, and now we're saying that you can't perform these implicit conversions for us. If we want to shift data, we will tell you. I as the programmer will tell you that I want to instantiate a shift data. You are no longer allowed. The compiler is no longer allowed to simply magic this const char star down here into a shift data. And so we will no longer call this. Yes, question.
Another way to circumvent this would be to initialize first a char array with the string and then pass the array as a variable, wouldn't it?
Yes, that's absolutely correct. If you had a mutable character array, then the overload resolution would pick the char star, which is harmless, just for clarity, this one here, and that would be fine, right? But the point is that you shouldn't have code that's surprising. So from a design standpoint, these things are best avoided, and the best way to avoid them generally is you use this. Oh, where's my mouse? Oh, it's going crazy. There we go. So the best way to avoid this is to use the explicit keyword on your constructors when they take a single argument. You can additionally do this for constructors that take more than one argument, and there is a niche case where it can make sense and be useful. I'm pretty sure I have a slide on it, so I'll wait till I get to it. If I don't, I'll recap on it later. Anyway, so we're done. That's it, fixed. Just add a keyword, all sorted.
Good question.
Question
About the similar thing but for different examples. So this was a string literal. What if there was a defined variable which was a string and you put that in an argument?
A stood string?
Yes.
You mean the standard library stood string?
Yes.
It would not compile. Because you have two overloads. One overload takes a const char star. One overload takes a char star. The other overload, let's go back. So one overload takes a shift data, one overload takes a char star. A stood string is neither of those things, and stood string does not have an implicit conversion operator to turn itself into either of those things as well. Right? So stood string is completely separate from these because it's not made convertible to either of them. It just won't compile in this particular case. Okay. So the gist of this is that C++ is going to try and perform an implicit conversion by looking for a compatible constructor, as in the example I gave you, or a compatible conversion operator, which would have applied in some alternative universe where stood string had a conversion operator to convert itself to, say, a char star. Right? If stood string had a conversion operator built into it, that would allow it to convert to a char star, your example would hold. But they didn't do that in the standard library precisely because all kinds of nonsense would happen. Specifically because actually mutable char stars are not allowed until C++ 20, right? Char stars are going to become, stood strings becoming mutable in 20, isn't it? I believe.
I think 17, there was a non-const data.
Oh yes, that's true. You can't change the size, but yes, you have data, that's correct. Anyway, that's a sidebar, don't worry about that. So, this only has, crashing into a slide, only has relevance for a constructor when the constructor takes a single argument, as we saw, right? Because if it took more than one argument, I can't just perform an implicit conversion with two arguments. That doesn't work because the first argument is a function, but then it's going to do the conversion afterwards. So it can only evaluate a single argument in that case. So it has to be a single argument constructor, and the constructor does not provide a default value for the argument. So instead of using explicit, you could alternatively have a default value. So if you take an int, if you have a constructor that takes an int, if you do equals 5 for that argument, then it's no longer considered for implicit conversions. But it doesn't make sense to do that unless you have a good reason to prefer explicit, unless you need to default it to 5, of course, or whatever value you want. However, a constructor taking multiple arguments can actually benefit from this. This is since C++ 11 that this has occurred. It didn't apply in older versions of C++. And it's still a bit niche, but it's included because it's good to know about, I guess. But essentially, it will suppress the copyless initialization. So for example, if you have a type called myClass, so why does it just fly off when I turn it on? It's going crazy. Okay, so if you have this myClass, and then of course you have the var value x, which is an instance. This won't compile if you mark the constructor for your type as explicit. So obviously this is just a constructor that takes an int, and an int, three arguments, all of which are ints. Without the explicit, this would compile just fine. When you put explicit on it, we're now saying actually no, I don't want to allow this for whatever reason you might wish to. I can't really find any good use cases for this. Maybe there's somebody out there who will tell me there is a brilliant use case. So for multiple argument ones, I still say it's a bit of a niche, really. However, even if you do put explicit on it, as long as you don't use the equals sign, So you do this direct initialization, that's fine. So the second line here is completely okay, that's fine, no problems. Right, so we're going to get onto something that I was mulling over, and given that actually in terms of writing object-oriented code, they are fairly crucial, I decided that I'm going to show you exceptions. So who here has familiarity with exceptions in either C++ or any language? Cool, okay. So those of you who do have experience with exceptions in other languages should find that the concept in C++ is pretty much the same. Well, we'll see about that. And again, another classic quote. I don't know who had this, but if at first you don't succeed, what is version 1.0? So, what are exceptions? Essentially, exceptions are a way to unwind to some prior points in the chain of calls that you've made, right? So, you know, function A equals function B, function C equals function D equals function E. And if I return from E, I just go back up to D. But if I throw an exception, I can jump all the way, unwind all the way back up to potentially all the way to A, or potentially further, but that may not be what you want, as you'll understand shortly. So, as I just said, it's a way of bubbling up out of multiple functions, right? So you call a function which calls another function, which calls another function, and if you throw an exception, you unwind backwards until something can catch it. So, as the name also suggests, this is designed for exceptional cases. You don't want to throw exceptions as a part of sort of natural control flow. It should be something that's not going to happen very often, if at all. Exceptions do not come for free, and as a result, using them compared to sort of having conditional handling does make them more. They are more expensive. So, generally speaking, again, avoid using them except for when it's a case that's actually extremely rare, and it makes sense to use those. So in essence, we utilize try and catch blocks for catching exceptions. So somewhere in your code, you mark out a try block, and then that try block must have a corresponding catch section in that same sort of area of where it's, so try, curly braces, followed immediately by a catch. And if anything inside that try throws an exception, it may go to your catch statement. It will depend on what you've put in your catch statement, which we'll also get to. But for now, just think of it as I have a try block, a corresponding catch block that lives in the same place as the try block. And if something happens inside the try block where an exception is thrown, the catch block can intercept it, depending on what you put there, which we'll get into later. And of course, so if you want to throw an exception, you use this language keyword, which is called, well, throw. Very intuitive. And when you use this keyword, you give it some object to throw. You could do throw 5, which means you throw an int. Probably not very clever. You could, usually in C++, which we'll also cover shortly, you have these base classes that represent exceptions, and you usually throw those, and you derive from them, and throw a derived type. We'll get into that very shortly. Is everyone okay with this so far? Don't want to go too fast.
Could you explain the throw part?
So, the concept. So throwing an exception, right? Usually you have some conditional case, right? So something has gone wrong, and then to indicate that it's gone wrong, you throw an exception. You throw an object, right? You can throw an int, you can throw a string. That's generally not what you're supposed to do. The language won't stop you. There is a base class in the standard library called std_exception. So you could throw std_exception because it's an exception. But you can also then derive from std_exception. You can have your own class that derives from it and throw that instead. And that would be useful because you can incorporate more specialized information into your exception. We're going to get into those details later. But the point of throw is simply that until we get to that slide, just think of throw as like, okay, something bad's happened, someone needs to catch it. Somebody needs to catch this exception I'm throwing, right? You don't know if someone's going to at that point, but we'll get into what happens if nobody does shortly. Yes, question?
I wanted to explain.
Sorry?
I thought you could explain it to me.
Well, if you've got
you say you're coming to the first?
Oh, never mind then. Okay, fine. Okay, well, if I don't, then do chime in. And yes, if nobody catches an exception, if you throw an exception and no code catches it, so most likely your own code, you don't have any try or catch, that's it. The standard says that your program must be terminated immediately. And that is exactly what happens. You just die. So let's have a look at a relatively simple example of an exception in C++. So first of all, we're going to want a function that will convert a number to a string. So the function's called b. Don't go crazy, here we go, laser pointer. Oh, that's good. So we have a function called b, takes no arguments, and it returns a std string. And of course, we can just do, std string x. Could have used auto really, but just to be explicit, I use std string. X equals std2string, which is a function that lets you convert numbers to a string, obviously. And it calls a function called c, which we're going to get into in a sec. And of course, we just return x. And that's it, close that function off, done. So now let's create c, right? The function that's going to generate this number that we then convert to a string. Well, okay, it's called c, it takes no arguments again, and it returns an int. But this one I haven't implemented yet, so I'm just going to throw an instance of this standard library logic error type. So obviously we covered inheritance already in the past few sessions. Logic error is derived from std exception. So the logic error class is derived from the exception class. It's generally good practice if you want to make your own exception types to derive from std exception or one of the other standard library types, because other developers can at least catch the exception type, the base type. But we'll get into that in a bit actually. So this is the simple example, right? Fairly clear. If you call b, it will call c, and then c is just going to throw an exception because I didn't implement that yet, right? So now let's have a main function that's going to call b, right? Oh, this is out of order, isn't it? Now? This is where my slides start to fall apart. Right. So we have, let's just go back there. So we have an int main. We start our try block. This is where we are going to run some code, but we can handle it. So we call b. So, oh, that is inverted, isn't it? Right. So we call b, and we're just trying to assign it to a variable. Obviously, b is going to call c, which is going to throw immediately. Fine. And then we'll try to print the string. Right? We're never actually going to get here, of course, because we know that this is going to throw an exception. So as soon as you throw an exception, that's it, you abort, right? We will never go to this line of code here. Does that make sense? Yeah? So then we close off the try, right? So that's the end of the body for the try statement. And then we begin the catch statement. You must follow a try immediately with a catch or it won't compile. So we take a const reference, which is the ampersand, to the std logic error class type, right? Which is this thing here, this object we're throwing, this class we're throwing. And I've given it, you can actually access it, it's a proper class, it has member functions and all that kind of stuff. It has a string member function. Yes, question?
So what would happen if it's const, not logic error or something else? Because you don't know.
What would happen if what?
If there is, because you catch through the logic error, but let's say if you don't know what's inside the C function, so you don't know that there is logic error.
C function?
Yeah, the C bracket control.
Oh, sorry, the function called
so
C.
basically, you don't, it's hidden from you. And if you use something else, what would happen?
So you wouldn't catch it, and your program would terminate.
Okay.
Yes, question.
But when you the whole idea of inheritance, when you just use the standard exception.
Yes, that's what
to
we
catch that one. So
Yeah,
just
that's what we're going to do. But this is just a simple example. So we have matching types now. So at the moment we just take a reference to the type that's thrown, the exact type that's thrown. We use const because obviously why would you want to modify an exception that was thrown? That doesn't make sense. So consequently we make it const correct, and it just says failed. Now usually if we wanted to read this string, so down here with E, there is a member function on that class called .what, and it will return .what.
The logic error class has that built in.
The what?
Has that member type built in.
Yeah. So what, I'm trying to sort of accentuate the pronunciation for the mic, but yes, that member function exists in std exception. It exists in the base class of the exception, and because logic error derives from it, it also has it. So you have to construct it with a string, and then somebody can access it through that member function. The what member function.
You stood out, e dot what. You get rid of the errors.
Precisely, you would, yeah. So in this case, we just say we failed, but the program won't crash, at least. That's good. And that's it, we've closed off main. So consequently, just to be clear, this line will execute this auto stir equals b, that will work just fine. We'll immediately throw an exception, so we will not execute the cout, okay, because an exception is thrown. We will instead jump here where we fail, and that's just a comment, obviously, it does nothing. And we just exit main with a, we would have a 0 return code, the implicit return that main has.
So we only know the exception was thrown purely through the throw keyword as part of that, as part of the logic for functions. As in, that throw keyword defined in the exception.
Yes, the throw keyword is the language keyword you use to log an exception. Yes.
Well, you have several different ways to catch, and depending on what you throw, you choose the correct catch. If you have several different errors to throw, and logic error goes into logic error.
So when you catch this std logic error, well, in this case, because he's catching logic error, he will catch only logic error or anything derived from logic error as well. We're going to get into the inheritance part in a second. Yeah.
Why have you got int c? Why do you return int?
So it's supposed to return an int. Obviously, I didn't implement it yet, so I just throw an exception, which is perfectly valid code. But the point was that it's meant to return a number, and let's go a bit crazy. It's meant to return a number here, right? And then this b will convert the number to a string.
Okay, so the int's nothing to do with the throw.
No, the return type has absolutely nothing to do with throwing. You can say that you return whatever you want. When you throw, whatever you choose to throw has absolutely nothing to do with your return type at all. Yes.
So what I'm saying, so confusion on what something I want to clarify is, I thought this was meant to be when this is meant to be undefined behavior, but this is hard coded in that. So your example is hard coded in to throw an exception.
So essentially, when you throw an exception inside any function that's meant to return something, it's a legal short circuit in the logic, and you either return, right? You either end up returning something and everything's normal, or you don't return anything because you throw. If, however, you don't throw and you fail to have a return statement, then yes, you have undefined behavior. Your program is then invalid.
So how would you then? I mean, you mentioned you've simplified the code.
Yes.
But what would be the logic in C? I mean, in this function C, that you would have one would be returning and one would be throwing, right? So what would be like if whatever your arguments or whatever you put in doesn't match X, Y, Z, then throw. So
it's essentially aborting the process, right? So we call B here, right?
Yep.
Which is fine. We go into B. We then want to begin an assignment. So before we can assign X, we need to call std toString.
Yes.
Before we can call std toString, we need to call C. So we first have to evaluate C. So the compiler calls C. It then immediately calls this throw, which means that we will abort calling toString. We'll never call that. We will never do the assignment into X. We will never, this never happens either. We just short circuit straight here.
I get that.
So what I think all he's done there is just to show the mechanism how you throw something.
Yes.
There is no logic in it.
Yeah.
So.
But what would the hypothetical logic be to use throw as well as return?
In C, do something and say something may go wrong. So what I'm going to do, if something does go wrong, I'll throw this. But if it doesn't, I'll just continue and then proceed.
So there's a condition where something has gone wrong. Sorry, I just need to check if I fixed my mic. Except it's not letting me. One sec. Where's the mouse gone? There we go. Okay, it's working. Cool. So, of course now I've lost the mouse off of there. So yes, in essence, that is aborting the flow execution. So let's look at some of the nuances though that are involved with exceptions, where it gets a little bit more, a little bit more complicated, but also a lot more powerful as well. So first of all, as with everything else in C++, as we've been learning through our OOP, exceptions themselves are strongly typed, and they are also part of the entire type system, right? All of the rules of inheritance hierarchies and interfacing, all that stuff, that applies to exceptions as well. You can use that. So consequently, when you throw some type of exception, right? When I say a type, I mean like the logic error class, right? Or your own class. You can throw a std string. You can throw anything you want. You can throw any type that exists in the language. Nothing stopping you. Obviously, that's probably bad for people if you throw something like a std string. The accepted idiom is that you will throw some type that is derived from std exception. It's a well accepted idiom, and everybody can work with that reasonably well. If you don't, then they'll probably just not know about your exception type, and they'll crash their program instead. So essentially, when you do throw a type, it's going to look for the closest. So obviously, I can have a try statement that calls a function, and then that function also has a try statement, right? And then that function, it calls another function that also has a try statement. So when it starts unwinding, it's going to look for the nearest try statement in the hierarchy, right? In the sort of layers of function calls. It's going to find the closest one, and then it's going to see what catch statement that one has. And it's going to see if, that's wrong. It's going to see if that particular statement has a matching type, a compatible type, right? So if you throw a derived type, does this closest one have one that catches either the same thing, same exact type, or maybe a base? If it's a base, that's great. That works fine too. So consequently, it means that you can use inheritance and interfaces for handling exceptions, right? If you derive from std exception with your own class, you can then throw that class, and I can either have a catch statement that catches my exact class's name, maybe I'll call it, Ollie's exception or whatever. So I can either catch Ollie's exception, or I can catch std exception, because of course Ollie's exception was inheriting from std exception, so it's a kind of std exception. That's perfectly legal. And as I've been saying, it lets you throw absolutely anything. You can throw any exception, any object you like as an exception. Integers, doubles, floats, chars, string literals if you want. You can do it, but it's generally stupid. The well-known, well-accepted idiom is that you will throw something that inherits from std exception, because they can call .what on it, and you can have some useful human readable string in there that they can see, and they can understand what sort of contract they must have violated in your library, or whatever code you've written, right? Or in your own code. And so this allows us to leverage the type system, this strict, strong typing. We can catch specific, the derived types, right, for very granular handling. Maybe I have an HTTP server implementation, and I have a derived class that derives from std exception or std runtime error, whatever. And this HTTP exception I can catch quite far down in my call hierarchy, right? Interacting directly with HTTP. And if this exception gets thrown, I can maybe try to recover, because I might be able to look and say, oh, I've got some invalid headers, but the content of the body was invalid. But then further up, the more generic layer, right? If a different exception type is thrown, so it's not an HTTP error, it could be a connection error instead. But at the top level, I don't need to care about this specific connection error. I could just have a generic handler for std exception. So someone throws a connection error, and I just handle std exception. But my rules are that if I get any kind of exception, something must have badly gone wrong. Let's just close the socket, kill everything off. That person, that client I was talking to that's gone away. So they've had a problem. Right? Oh dear.
He threw it.
Yeah, well, the TV's just thrown an exception, yeah. Or it's exploding, one of the two. Can we get it back?
We are still okay on
It's Yeah, YouTube should be fine, but
It derives from student
there we go. Okay, we're live again. Radio interference or something. So yes, the generic handler can just sort of kill off some client's entire section, essentially. And we can also rethrow from inside our catch statement. So imagine in this HTTP exception case, there's sort of the close one that handles the specific HTTP exception. It can do some handling, do some logging, and then inside that catch block, you could just put the word throw. Nothing else, just if you want to, you could throw something different. If you put the word throw on its own, inside a catch block, you're saying, well, I've done a little bit of stuff, but I can't actually truly handle this. I want it to go up to the next level. So you do whatever you want to do, but then you effectively, it's called rethrowing. So that's it, you come out of your try and your catch, you've done your best, but you couldn't sort it out. So it'll go out of you and up to the next TryCatch block to see if they can sort it out. And they may choose to rethrow the same object as well, and it can keep going up until, well, there's nobody left, and then your program just terminates. But the point is that you can rethrow the exact same thrown object for inside your catch statement if you wish. Is that clear?
But why are you throwing?
You
just type throw.
You just type throw. This is only applicable inside a catch statement. Then the exact same object that was originally thrown, nothing changes. That exact same object is just passed up to something further up the chain,
Which is ready to catch it.
which is obviously ready to catch it. Yes. Question.
But this can only apply as long as the exception is thrown within the context of a try or a catch statement. If it's not, like,
You can only use this throw and then nothing after, like throw semicolon, right? Just the word throw and a semicolon to terminate the statement. You can only do that in a catch block.
Yeah, I mean generally when you use throw, for example, if you have a program and you throw outside of the context of a try block for the first time, does it still try to find a proper catch block, or does it automatically terminate?
So every time if you're asking about the implementation, every time you declare a try block, internally the compiler is generating a table of handlers. So each try block registers some new handler, right? So that try block, that's one handler. Then inside that try block is another try block that registers a new handler, right? And the types it will accept. So if there's nothing registered and you throw an exception, it just terminates. There's no the table is empty. There are no handlers registered, so just terminate the program. That's the implementation. Does that answer your question?
What if the throw is outside of the try statement?
It's
So
outside
there
of
is
any try statement.
Yes.
Yeah, it just kills the program. You just crash. Some implementations try to help you a bit. So on if you compile with GCC, it will print to the console the exception message, as long as the exception derived from std exception. So some implementations are kind of helpful.
I know in Java, for instance, in the function signature, it has to say this function will throw an exception.
Yes. Yes, that's correct. In Java, you have to put the throws, whatever at the end, throws throwable. You know, throws exception. No, it's not. So in C++, the closest thing that exists is the no except keyword. You can promise that you won't throw an exception. However, that is merely a promise. If you throw one anyway, you bypass all exception handling and you just terminate the program instead. So the compiler won't go, oh, you threw an exception, but you promised not to. It will let you compile, but then you go straight to terminate. Do not pass go, do not collect $200.
Does the no except go down to the derived class?
No, it's not infectious. So an individual function can declare itself no except, right?
Why would you do no throw? No except, sorry.
You're essentially making a strong guarantee to somebody that your function, your constructor, your member function, whatever, will not throw an exception. It means that if you do somehow throw one, you have a bug and your program's just going to crash. Yeah.
But inside the function, you can only call other functions. functions which also have a no except.
No, you can call other functions which are not no except. That's fine, because you could put those in a try block, right? I can have a no except function, which then has a try block inside it, which will then call some functions that may throw an exception. And my no except function will not violate its contract as long as it catches the exceptions of anything it's calling. Then it's fine. Yeah.
So one of the things I understood about more exception was that you may do something that'll throw an exception, so you put in a TryCatch. But the whole point of the as you said before, the exception handling, or so the program doesn't terminate, or you define the behavior once you come to an exception. So, for instance, like dividing by 0, if you're a math doing maths, which is a classic one. If you have a denominator 0, you say, you know what, no, you're dividing by 0. But I can move on from it. The program doesn't have to terminate. I can say, listen, if you're doing inputs, you're putting a divisor that's not acceptable. Try again.
So floating, yeah, dividing by 0, floating point exception, yeah. I mean, floating point exceptions are not strictly C++ exceptions. They're their own machine level thing, but there are compilers that will massage it into an exception for you. Yeah, they're not. That's floating point exceptions are not strictly speaking part of C++ exceptions. Unless Tristan wants to disagree.
So,
C++ exceptions are not the same as floating point exceptions. But there are environments that will massage them into a C++ exception for you. Microsoft, for example, has this. No, is this alive? Yeah, cool. So you can also make an entire function's body a try block. So obviously, you know, a function has those curly braces for its body, right? Opening curly brace, closing curly brace, and then code. Well, you can stick the word try in front of the opening curly brace of the function. And then the entire function body is a try block, which then logically follows that after you've closed the function's body off, you have to have a catch after it. It looks weird. It's a somewhat esoteric feature of C++. It can be quite useful. I've used it in several places. It's not hard to understand, I would say. It's probably a bit simpler than the nested try block. But it can be very elegant for some designs. So let's have a look at one. A type-oriented exception example, I'm calling it. So let's randomly throw 2 different types entirely. So we're going to demonstrate the inheritance aspect of exceptions as well. So I'm going to have a function called random throw. Is this working? Cool. So it takes obviously an argument that is I call it random number. It's just an int. It returns an int. And if the number is odd, so it has a remainder of 1. If you divide it by 2 and it has a remainder of 1, it's odd, obviously. So if that is the case, let's throw a stood logic error. The word logic exception. And if it's even, we will throw stood runtime error. You notice I don't have an else statement. Fairly obvious why, right? Anyone want to chime in and just say why anyway? Why is there no else statement?
So only one condition. I mean one. You're executing only one thing.
One will happen.
Yeah. Because obviously a throw is a terminating statement, right? If we throw stood logic error, then we've terminated execution in our function. We'll never get here because this effectively terminates the entire function's processing. And there we go. We've closed that off. So now let's have a function level TryCatch that will call it and handle it. So as you can see, there's only one difference in this function declaration. So it returns a std string. The name of the function is random num2 string. It takes no arguments at all. This is going to move, yeah. And we just put the word try there. Super simple. And then we just open the code body as you normally would. It's just got the word try inserted. So if you look, this function does not have it. This function does have it. And we return std2 string again. But we call random throw, and we just call the crand function. I don't like using this function, to be honest, but it's just exposition and it's nice and short, so it's some function that returns a random number, okay. And then we have our catch. So the notable thing here is that we have entered the body of the function here, right? And we've ended the body of the function here. But we do have a return type. This is where it gets kind of interesting, right? Because our function does have a return type. And now we have caught the exception. So consequently, we still have to return. This is sort of like imagine this is like, if everything is fine, you just execute the body of the try, and nothing goes wrong. So you just return this stuff. But if something goes wrong, the catch is now going to act as like an alternative function body. Because an exception occurred, we now have this alternative function body to use. So we still have to return a string. So in this case, we return logic error. Yes. But
you didn't define a throw for it to catch it back to something in the language string.
Sorry, I'm not following. There's a throw here and here. There's two things we can throw. Depending on the number, we might throw this or we might throw this. The runtime error.
Can you have multiple catches? What about the runtime error?
Guess what? I didn't do it. Damn it. Okay. So to answer your question, I could have sworn I'd done that. Yes. So you absolutely could have multiple catches. So after this closing curly brace, you could write yet another catch statement which would catch std runtime error or whatever. But yeah, I remember I wanted to demonstrate now. So it was the nesting. Anyway. So in this case, we only catch just logic error, but you could have yet another catch statement that will catch another one and do something different. So in this particular case, this function is only going to return you something if, well, either no exceptions are thrown, or if there's a logic error, then it will return the string logic error. If it's the runtime error, it won't handle it, and it won't. Yeah.
So what we're basically saying in the first one, if we have any kind of exception that any illicit exception that happens, we'll terminate the program because there's no catch handles unless something else handles it.
Based on code currently on the screen,
Yeah, we'll just terminate.
if it throws runtime error, without seeing anything else, it will terminate it.
Whereas the other one is handled, you can see explicitly it's being handled, as opposed to saying that
You
something
can
else
see,
handled.
yes, you can see that logic error is explicitly handled here.
So therefore it doesn't terminate the code.
Correct, because obviously we catch it and just return normally logic error. That's fine. So this represents an alternative return type, return value for the function. Right? Either give you std2 string of the number, or the string that it returns will be logic error. I mean, we know that this function here never actually does return anything, so consequently, yes, we know that that's actually a useless function. Yes. Oh yeah, that's fine, of course. So let's add a main to call it, and again, this is out of order. Come on. So here's the main. We now have a try block. I can't remember if it's legal to have the try on main or not. So, obviously we're going to call the random number to string. We'll assign it to a variable we're going to call stir, and we'll just print it out, of course. Of course, well, we know that we might end up printing it out if it's a logic error, because it will just return that. It's the only case where it could print out something. But otherwise, we'll catch a constant exception reference. Note that it's a reference. So an important thing to know is if you don't take a reference, then you end up doing what we covered last week, which is slicing exception objects. You end up constructing a copy of the exception someone threw. So you pretty much always want to take a reference to the type, because you don't want to slice it in half and construct a base from the right. And again, just I failed, do nothing, I'm happy, phase. So just jumping back to my slides, my bullet points rather. Obviously, depending on the random number, it's either going to be logic error or runtime error. And obviously, yes, the reference is very important. So just bear that in mind. Pretty much always want to just take a const reference to the type. There's no real reason not to do that. I mean, the const is for being const correct, right? Why would it make sense to modify an exception in a handler, right? Because when you change what the exception says it is, that doesn't sound right. You should be reading it, you shouldn't be writing to it. And that's essentially it. And this works fine because now if we throw a logic error, we'll go here. If we throw a runtime error, we will go here just fine. Which means that std runtime error must be what attribute?
Derived from the std.
Bingo, yes. It means the std runtime error must be derived from std exception, since I told you it will work. And it is indeed. It is derived from std exception, so it will work just fine. It will not crash the code. So let's just go into the usefulness of these exception points. So when we handle some specific exception type, an exact type, then obviously it enables us to tailor our code to that particular event, issue, whatever you want to call it, right? You know the exact thing that went wrong, so you can respond to it accordingly. If you have a generic type, right, you've now lost information, right, because it's some base type, so you don't know exactly what went wrong, but you know something went wrong, right? So if you were designing a web server, for example, right, in C++, then you would think of the specific exception handling as being like, oh no, it's freaking out again. Okay. You would think of the specific exception type as covering something along the lines of, a bad HTTP header. Well, if they send a bad HTTP header, probably just move on and ignore it. But then if something else goes wrong and you end up at the std exception level, right, the top level sort of handler, you don't really have enough information anymore. So most likely, you still don't want your entire program to crash, right? If you have a web server and thousands of people are connecting to you, and one of those people causes you to throw some exception that goes to your top level handler, you don't want to just crash your entire program because one person sent you something bad. You just want to get rid of them, really. So your top level handler would probably just close the socket to them, right? Shut the socket off. Bye bye, they're done, and move on to servicing the rest of the clients. And again, you can at least report it. The std exception has this .bot member function. You can put that to a log or something. And again, failing to handle an exception will kill your program. So when I was saying just a minute ago about having a top level exception handler, if you are going to leverage exceptions, have something right at the beginning of your program, in main possibly, right? Or if you're multi-threading at the entry point of your threads that can handle std exception, possibly even handle what we call the ellipsis, so ... You can catch ... which will catch absolutely everything. The problem is that you can't see it. So you have no idea what was thrown. You can't inspect it, you can't do anything with it, you just know that some exception was thrown, but you have nothing to look at. So usually you will catch the exception first, and then have a catch ellipsis for the cases where something really stupid has been thrown that doesn't derive from the exception. Generally speaking, if you're a good programmer, they will, or other people are good programmers, they will derive from the exception. If they fail to do that, you can still use the catch ... the ellipsis, to handle those dark extreme cases. But ideally, you should never see that in practice. Yes.
So is it a bit, so I'm just thinking of the implementation. Would you use exceptions when you're having to deal with, let's use the word interfaces, with third-party stuff that you don't actually, is that a good rule to only use exceptions when you're dealing with stuff that you can't actually specifically control inside the program?
So the question was, should you use exceptions when dealing with third-party stuff inside your program?
Well, it's third-party coming into your program, so if it interfaces it.
Oh, I see.
Not in the terms of programming.
I get it. Yeah. So are you talking about using third-party libraries, and do you throw the exception, or
any data or anything that you can't have very tight control over?
You can't have. So you're the library in this case. You are the third-party program. Yes, generally. So if you are a third-party pure C++ program, throwing exceptions is a completely viable and valid way of indicating that the person using your library has goofed. It is a design decision. There's two camps in C++. There's basically people that think exceptions are okay and they're acceptable, and the ones who think that the overhead is too much to bear and don't use exceptions, have error codes or some alternative. It's one of those cases where there's many ways to skin the proverbial cat. Personally, a lot of libraries I use, they either use exceptions or they offer you separate overloads. So Boost ASIO, for example, has function overloads where one of them will just throw an exception if you did something wrong. It has a separate overload where you pass it an error code as an argument. We pass an error code as an argument instead, and you won't throw an exception. Come on,
That was me just generally.
Oh, we
But
had
I would
that.
say one of the problems with
Okay.
if you are writing a library for other people to use, and you're going to throw exceptions from your library functions, you need to document what exceptions your functions may throw. Right? Because if somebody else is using your code and you throw a, I don't know, out of range exception, whatever it may be, something that's specific for your library. And then in version 2 of your library or version 1.1 of your library, you can throw an out of range exception, or you can throw a different kind of exception. Well, if you haven't documented that change somewhere, the moment you throw the second new exception type, the person using your code hasn't accounted for that. That exception's going to bubble all the way up, and they eventually crash their application.
So the statement, sorry, just to repeat that for the YouTube, the statement was that if you are going to throw exceptions in your own library that you're going to release for people to use, you should document the types of the exceptions that you throw. And I would add to that as well that make sure that they derive from std exception, because in the worst case, if they can't plow through your documentation, they can at least catch std exception and read the .bot member function to have some human readable information as to what went wrong. Yes, Michael Berry.
I've seen a very interesting alternative to that, which doesn't interrupt the flow of programming that much. It is when you define a function and you know, for example, that you're using a third-party library which has maybe a very extensive structure and something can go wrong, that the return type of your program is actually an enum, which takes two values. The first one is the OK value, so the expected return value, and the second one is a possible exception that has been thrown away. So in your main program, you actually unwrap that type, and it will return to you whatever has been returned by.
So what you're talking about there, just for those who are watching, he's talking about a case where you have, I'd rather use the word variant. Maybe that makes more sense. So essentially, you can have a function where it returns a variant, which is either the expected type, the normal return value you want, or alternatively some other type that represents that something went wrong. And it's funny that you talk about this because there is a paper for C++, which we is it static exceptions? I can't remember the exact terminology that was used.
Exceptions, throwing values.
Yes, static exceptions, throwing values, and it is basically exactly what you described, which it means that unlike the current form of exceptions that I'm describing in these slides, this proposal means that, much like Java, a function must explicitly declare what it will throw. It can't just do this magical sort of bubbling all the way up.
No. It only has to say I will throw it, doesn't.
Oh, sorry, yes, that's true. It has to say that it throws it, doesn't it? Well,
Because there are no types.
well, that's right, because it has a magical type, but that's controversial, so I'm not going to necessarily.
It's not. It's the way it has to be.
Okay. But yes, magical library types, I hate them, have a big issue. But that's not relevant to this lesson, so don't worry. This is potentially future C++. But yes, that is actually something that's coming down the pipeline. So very interesting bit of information there. But back to what we currently have in C++. Failing to handle an exception, as I've said, will kill your program. And again, to reiterate on this, everything between the point of throwing and the point of catching will be destroyed, will be destructed in the usual clean manner. They will die, will be wiped out. And this could actually be useful to you. So imagine we have a transaction, right? So we're writing some financial software. It's going to credit some amount of money to one party, to one account, and it's going to debit some amount of money from another account. Right? Those are two operations we have to do. They must be atomic. If we credit one, we must debit the other. We cannot credit one without debiting the other. But imagine this is some distributed network-based system. So that counts as a transaction, right? We must either do both operations or none of them. So there's two ways we can do this, right? So obviously we could use exceptions, or if somehow doing the transaction goes wrong, maybe there's not enough money in the account to do the transaction or something, we can represent that with an exception. So obviously if we throw the exception, we're going to undo all the objects we've constructed, right? So imagine I had a class that represented the transaction, right? And when I constructed the class, I would give it 2 accounts, and then I would call, transfer money, right? When I call transfer money, I tell it how much, and it will attempt to debit X amount from one and credit X amount to the other, and then potentially either in the destructor I could then commit the transaction, or I could have an explicit member function that I as the programmer have to call. So I would call commit to commit the transaction and make it happen. But there's a slightly more advanced way of doing it. So yes, you could just use commit, right? So obviously if an exception's thrown, we'll just never call commit, because the exception will go out of us, destroy the object, and we never get to call commit. Cool, it's aborted, no problem. Alternatively, this is a more advanced technique, but actually not that difficult. In the destructor of the transaction class, there is a standard library function it could call. And that standard library function tells you if you're being destroyed because of an exception, or if you're just being destroyed normally. And we could technically do it that way, right? We could say, are we being destroyed because of an exception? Oh, okay, this is the abort scenario. Reverse the account balances. Or, oh no, it's not because of an exception, so fine, just commit it, write it to this, whatever. So, this is a use. These are use cases, right? This is just a use case. You can use exceptions to whatever you want. Again, try and restrict it to rarely occurring exceptional behaviour. Yes.
What's the commit call?
Could be anything, right? If it's a bank transaction, maybe it writes it to a ticker tape, maybe it writes it to a hard disk. The point is that you say add money to this one, subtract money from this one, and that's maybe say just in RAM, in memory. And then when you call commit, it then flushes that to the disk, the database, the ticker tape, whatever, right?
So in reverse, would you want to put a logic in to reverse the transaction or whatever? So there's an exception.
So no, because essentially if there's an exception, you will never call commit. Or if you call commit and commit itself throws an exception, that will also abort it, right? The point is that you tell it what operations to queue up, you then call commit, and providing no exception is called at any point, commit will finish and it's done. But if an exception is thrown at some point, you'll just abort out of this. So you won't get to call commit, right? You'll just you'll never reach the line that says commit.
Right.
Yeah.
These are kind of rollbacks in the transaction.
Yeah, similar to a rollback, exactly, but it's sort of become enforced through throwing exceptions. We're just talking about a technique here, right? This is just a technique. This is not anything intrinsic to the language. It's just these are just techniques you could utilize. And so this will segue into something else I'm going to cover. You can throw exceptions in constructors. You can throw an exception in a constructor, and it will prevent your class from being constructed. It has several uses.
Is that in the curly brackets?
Correct. Yeah. Well, okay, there's a bit more to it than just that, but yes, that's true. So, on that note, further constructors. And another great quote: software and cathedrals are much the same. First we build them, and then we pray. So, construct all the things. Yeah. As those of you who've been with us before who've done the exercises hope you know, a constructor looks and works similar to a regular function, but no, it's not the same as a regular function, right? It has no return type. It can't return anything. It doesn't return because it's not a normal function. Yes, it has a body of code, so the only similarity it has to a real function, a normal function as it were, is that it does have a body of code, right? And it can take any argument you like. It can take as many arguments as you like. It can take none, right? That's what we call a default constructor. So it's still quite similar to a function, but it's still not quite the same either. And it's obviously what we use to set up the state of our class instance, right? We want to call, we have to call some constructor, and in that constructor it's going to set up all the member data, run any code that it needs to run to get itself usable, and that's it. And of course, just like function overloads, we can have constructor overloads, right? You know, lots of standard library classes have overloads. You know, std string has several, right? You have the default constructor, it doesn't take any arguments. It's an empty string. Has one that takes a string literal, right? It will initialize itself from a literal array of strings. It has one that takes a single character and a number. So I can put, you know, C as a character and then 500. Now I end up with a std string that's got 500 letter C's in it. There's a few more, but I can't remember off the top of my head. You get the point. And so the point of a constructor is to set up your class's data and just do any preliminary work that you need to do, right, to make that, put that class in a usable state. So you make sure that your constructor takes whatever arguments you need so that you can construct it, and then make it useful after it's finished constructing, right? Again, as I said in the previous session, yes, you could have a constructor that doesn't take any arguments, but then after they've constructed the instance, it's actually useless until they call, you know, initialize. So you have to call initialize after you've constructed it, which is silly. It's just something that somebody's got to remember to do. It's bad design. Your constructor should take the arguments it needs, and once it's constructed, it should be ready to use. Don't have these bad patterns of requiring additional function calls, like member function calls, in order to make your class really usable. You can, but it's just bad design. So, onto this segue bit, preventing construction. So let's imagine we have a constructor that's going to take a string as an argument, a std string, right? So we're gonna store that. We're gonna do something with it later. You know, they'll call some feature, some function we have to utilize that string. Well, it might make sense to us that we probably don't want to allow someone to construct an instance of the class if the string object they give us, the std string they give us, is empty, right? So I can default construct a std string and then it has nothing in it. And maybe when I say, okay, pass me a string, it could be someone's name, a student's name, right? If they pass me, you know, first name, last name, and it's empty, probably a mistake, right? No one has no name. So consequently, I can use exceptions to indicate to the programmer who's using my class that they made a mistake. And we can do this by throwing an exception. So as you've learned with exceptions, it's abortive, right? It will abort the further execution of a function. Not only does it abort further execution of functions, it will actually completely abort the construction of your class type. Anything that was already constructed will be destroyed. So if we throw in the body of our constructor, that will then obviously unwind and destruct all of our data members. They will all get unwound and destroyed. Additionally, though, of course, any of our data members, when we attempt to construct them, they might throw as well. So imagine I have a std string as the first data member, a custom class as the second data member, and then another an int as the third data member. So we construct the std string first. That's the first one in the list, so that's okay. Then we have this custom class, which has a constructor that happens to throw an exception because it didn't like us, whatever. So we never got to constructing the element below it, so there's nothing to destroy there because we never actually got past the second one. So as a result, it will destroy the std string. It will obviously, you know, whatever's in that class will get unwound, but that's a detail. It will destroy the std string above it, and then the exception will continue forward backwards to whatever is able to catch the exception. So consequently, yes, you can directly throw yourself. Also, any data objects you have in your class may also do this as well. You don't need to be aware of them. You can be blissfully unaware that they will do this, and it's somebody else's problem to catch it in that case. And again, there's no special rules to this. You either handle it or your program terminates. That's it, game over. And so, of course, it's probably better in most cases to use the type system to prevent somebody from giving you this sort of undesirable input, right? And so as an example, we don't want an empty string, right? So we could just make our own type that wraps std string, and it will never allow itself to be constructed with an empty string, right? Okay, potentially a malicious programmer could try and find a way around it. Usually you're not dealing with malicious programs. You could make that class for exceptions, but the point is that you could never use the type system just to make it fail to compile if you know, the type isn't exactly as it should be. So, but exceptions are a valid option. So it depends what the case, what the case is and what's allowed, right? You know, if I said you must give me a number between 100 and 200, well, I could take an int, but then if you give me something out of range, I just have to throw an exception. Whereas, okay, this is overkill now, but I could have a class type that represents 100 all the way up to 200. Right, so I have a unique class types that represent those numbers, or any num. Okay, or any num 100 to 200, and then there's no way somebody can go out of range because there's a strictly defined list of valid ranges. Again, that's somewhat overkill. It's not the best example, but you get the idea. But again, exceptions are perfectly reasonable. But if you can do it at a compile type system, I prefer to do so. So let's have a look at a throwing constructor, because, well, we've looked at exceptions. So I figure that let's just have a class that will wrap the std string with a safety check, much like the scenario I was talking about. So first we need our class, obviously. So there we go, class string. It's got a public section, close it off. And now we'll add a string data member to it. Private, obviously, default private in class. And now just an accessor function so that, you know, somebody who's using our class can actually get at the instance. So, you know, we have a function called get, doesn't take any arguments, it returns a constant string reference there, the little ampersand, and it's const accessible, of course, but we can use it even when you have a const instance of our capital S string class. And it just returns the member, this thing here. And done. So now let's do the constructor with a safety check. So of course the name of the constructor doesn't return anything because it's a constructor. The name must be exactly the same as the class's name, which as you can see it is. It takes a const char pointer, const char star if you like, called chr. And now we have the safety check. We don't want you to pass us a null pointer, right? You must pass us a valid character array. If you pass us a null pointer, or null, that's bad. So if you do that, we'll check it, and we'll throw a std logic error to say, well, you've messed up. You gave us a null pointer. That's not legal. Otherwise, we will just assign the string from the pointer. And this is actually a sensible, real-world thing to do, because if you do try to initialize std string from null pointer, const char star null pointer, that is a null pointer rather, it will crash horribly. Give it a try. Yeah, it will.
Because we won't standard library.
Right, I don't. There's nothing in the standard that says it has to be nice to you. So, yeah, I believe that Microsoft. Yeah, I think it's Microsoft. I think Microsoft have a nice check, but on Linux it will usually be horrible. So this is actually a sensible, real-world thing to do. That's. Sorry, I don't want to go too fast. Any questions? Yes, no. Is that clear?
We just run through the whole operation of the code.
Okay, so we obviously have our class string. It has one member, which is a std string. It has a constructor, which takes this one argument, which is a pointer. Right, so pointers can either point to something, or they can point to nothing, which is the special null pointer value. Right. So in this case, if you gave us nothing, we will throw an exception to say that you've given us an invalid value. Otherwise, you know, it's okay. We just assign the char array into, we assign that into the string, or the empty string object, to give it a value.
Yeah.
And then this is obviously really not important for the purposes of this
So that's a member function.
That's just a member function called get. It's not important for the purposes of this example. I just put it there for flavour, really, because I mean, this class should at least have some kind of purpose, right? So if it didn't have this member function, you wouldn't be able to read the string object.
Do you not really any try or catch?
Doing what?
Just throw.
Oh, I see. So because this is just a class, right? I am defining my contract, right? So you must not pass me a null pointer. So whoever uses it, yes, they should use a TryCatch. They probably should use a TryCatch. But it's still useful even if they don't, because yes, the program will terminate. But on the bright side, on most implementations, this will get printed to the screen, to the console. So if someone does make this mistake and screw up horribly, at the very least, they'll probably see this somewhere and see that they messed up. It's better than the alternative, which is that if we didn't do this check at all, then this would just crash horribly on most platforms.
Thank you.
So, how am I doing for time? Cool, yeah. So constructors, in summary, they initialize a class instance, and the most important part is it should make it ready to use. Right, it should be good to go. What that means necessarily can potentially be up to the user of your class. For example, I can default constructor stood string, right? But that's my choice. Stood string doesn't make me do it. I can choose to default constructor stood string, and I know it's empty. Right? I know there's nothing in it. I can't read it. I can stick stuff in it now. There's nothing in it yet, but I can't read anything because it's empty. Right? That's illegal with a crash. But that's my choice as the user of the class. So allowing someone to decide what ready for use state they want, that's okay. But never ever design a class so that they must call a specific member function after they've constructed it. Do everything in your constructor. And as I said, they can be overloaded. Right? Multiple different inputs, nothing, transtar, int, whatever you want to convert, right? So it doesn't really matter, but you get there. And again, by throwing an exception, we can abort this entire process, right? If either we do it directly, or potentially one of our data members is gonna throw the exception, then that's it. Our instance will not be created instead. Now, if it is one of your data members, then you have two options really. One is you can do nothing, of course, right, and make it someone else's problem, or potentially not someone else's problem. Depends if you're building a library or a whole application really. But you can choose to do nothing, and maybe it's not your fault. Alternatively, you could have a TryCatch. So it does get a bit more difficult with data members when you do this, because you'll usually want to create like a static member function that will try to do the construction. So obviously, in the initialize list of a constructor, you can't put a TryCatch there. But you can obviously initialize a member by calling a function that returns the type yes. Question? The entire initialize list. What's the syntax?
Exactly as for the function try. Constructing them, try.
But at the point of the try block, the data member is already initialized.
No. You can't catch exceptions. Like you said, you can't swallow exceptions in the initialize list, or you can do is reflow. It is possible.
So you're saying that the initialize list will go to your catch? Okay, work on that one. That's interesting. Okay, that's very interesting. But the way I've generally done it myself is that I would have, say, a stood string, some type, probably not stood strings, rarely throws, but say it's a stood string for argument's sake. And I would initialize it from a static member function or some kind of member function, or just some function basically, that will have the TryCatch block. So if we try to construct it from some data and it throws, we can try and construct it from some other data, some other alternative data instead. But yes, again, it's a matter of choice, right? Is it your problem? Is it your job to make sure it constructs everything constructs successfully, or should you just do nothing, make it someone else's problem? Depends on what you're building. So, before I go on to the next section, is that all good? Cool.
That's good.
Okay. So, operator overloading. This is now obviously revisiting something we covered weeks ago, I think, and restating the quote. But any fool can write code that a computer can understand. Good programmers write code that humans can understand. And this is where operator overloading is great. So, well, helping your fellow programmer, really. The operator overloads are a way to mostly provide convenience. And you'll understand why I say mostly in a second. And it's good for you and it's good for other people, right? They allow you to shorten syntax, which I'll show you in a second. For example, A equals B. Everyone knows what that's doing, right? It's got some variable called A. Oh no, is the laser? No, there's the laser. So obviously, you know, A is some variable. I want to see if it's equal to B, which is some other variable, which is a lot more readable than A dot equals B, right? I mean, okay, yeah. Those of you who do Java, sorry, suck it up. We're all aware that's how you suffer with life, but this is much shorter, much nicer, right? Well, C# as well, to be honest. So, and also for anyone wondering, you can do this in C# and Java, but it doesn't mean the same thing. If I have two Java or C# strings, doing this is actually comparing the references, it's not comparing the actual values inside them. So in C# and Java this is wrong, but in C++ it works just great. So we have a defined list of what we're actually allowed to overload in C++. So obviously, as you can see in my prior example, equals is obviously one of them. But unfortunately, overloading some of them is actually a terrible idea. It doesn't make sense. And a good example of these is operator comma. You can have A comma B. You can actually overload that. Probably doesn't really do what anyone wants or expects. And you can overload the ampersand operator. Again, another really terrible one, because if somebody is coming from certainly C, or at least a C++ programmer that knows his stuff, the ampersand operator should be getting the address of the object. And in fact, because there are so many people out there who think they're really clever and know that they're better than everyone else, who have used this one in particular, the operator ampersand, there is a std address of. There is literally a standard library function that will guarantee you it will get the actual address of an object, and it will never ever ever call some smart-ass's operator ampersand. Such is the level of disgust and hatred I have for not just these two, in fairness, but they are the biggest offenders. So yeah, there's ones that make sense to override. Equals is fairly obvious, right? As long as you don't do stupid stuff with it. A comparison operator should simply read, right? It would read A and see if the data inside it is matching what's in B. You could make it do something really horrible, like, I don't know, print some ASCII to terminal, or it's just running some code, right? Operator overloads are just functions. You could make it modify the class. Yes?
Could you give them two different types, two different class types, which have multiple members?
Yeah, absolutely. You can.
So what? It will by default look at all member types.
So well, all you're doing is writing a function. That's all you're really doing is writing a function. And you can have multiple overloads of that. So you can have an operator equals, where it takes its own type as an argument, so it will compare the same type to itself. Then you can have another definition of the function that compares a string, and have another one that compares an int. You can just make them up. You're just writing code. That's all you're really doing. There's no magic here. There's nothing magical about operator overloads. But even though there's nothing magical about them, you can do really stupid and insidious stuff with them because they are just functions, really. And on which note, think of them as just a lookup table, right? The compiler sees that we've got some class A, right? Because you can do it with std string has the equals operator overloaded. All the compiler's really doing is it's saying, well, what's on the left-hand side? Oh, it's a std string. Does std string have an overload for operator equals? Oh, it does, cool. Or call the function then, and give it B as the argument. Obviously, the type of B must match the argument type. So, as long as B was also a std string, it would work. The std string has an overload for comparing to its own type. Or it could be a const char star, has an overload for that as well, right? So, again, these are just it's like a lookup for some piece of syntax that you want to call. So, let's relate them to OOP. And when you're creating overloads for your own class, there's basically two ways you can do this. One of them is a member function. It's probably I recommend starting with a member function usually. It's going to be a lot easier because usually your operator overloads probably need to look at private data, and so it's simplest if they're just member functions because they're allowed to do that. They're part of the type, part of the class. It's legal to do that. But alternatively, so yes, it's the easiest trick. But alternatively, you can use a free function. So this has nothing to do with class, it lives on its own. It just has, operator equals, argument A, argument B. So argument A can be any type you like, argument B can be any type you like. But it's not part of the class anymore. And of course this makes sense in cases where you're going to deal with two different types, because it means that if you flip the types around, so if you have like string and int, then if it's a member, your string type would have to be on the left-hand side, because an int's not a class, obviously. So you can have a member function that takes an int, but then the string has to always be on the left-hand side. If it's a free function, it doesn't matter which side is the string, which side is the int. The caveat is that obviously a free function is not part of the class. So how would you maybe work around that, anyone? Based on previous lessons? If you want to use a free function to overload an operator, what possible keyword in the language could help you get around the issue of accessing private data?
Friend.
Bingo, friend, thank you. Excellent. And yes, make it a friend of your class if you need to. So they are still just functions. There's no real magic to them. It sounds fancy, like, oh, I use equals, but somehow it's just going to this operator equals thing. Well, actually don't overcomplicate it. If you look at what equals consists of, right, it's some argument on the left, some argument on the right. Well, if it's a member function, then the argument on the left is, our instance, this. And the argument on the right is the one we're going to pass to it. If it's a free function, however, right, it's not part of the class, well, the overload just takes two arguments. And then it doesn't matter what's on the left or right, because the compiler can just interchange them. If the one on the left is a string, well, that'll be the first argument. If the one on the right is an int, that'll be the second argument. If they're swapped, it'll just swap them over for you. But that doesn't apply to member functions. Member operator overload functions. And because they are just functions, you can actually call them directly by their full-blown name that you use to define them. So you can, rather than using equals, you can use the word operator equals, parentheses, and then whatever arguments it takes. You don't have to just use the shorthand syntax. You can literally write the full name that you define the function with, operator or whatever. Sorry?
That defeats a lot of the points.
Absolutely. It generally does just defeat the whole point. But to demonstrate to you that there is nothing really massively magical about them, you can do that. And again, if they are a member function of a class, they are just like any other member function. They can access private data. They can call other private member functions. They're just like any other member function of a class. So let's have a look at a convenient class. So I think I didn't bring up C-line, so I might need a second for that. But there's obviously a lot of operators that you can overlay, right? Huge amount. So I'm going to go through some code that overloads quite a lot of them. And when you look at these, look at them individually. There's a lot of code you're going to see now, but each individual function is doing a different thing, and that's the part to focus on. And so yes, we're going to look at a class with a bunch of overloaded operators.
You overload operators tend to use references.
Sorry?
You overload by reference.
When I
You overload by reference.
do I overload by
Yes, operator overload.
So my mouse is currently trapped inside a window, which is somewhat annoying. How do I get it out? There we go, got it. Okay. Where are you? Sea Lion. And let's move you to Right. That's not doing what I want, is it? Well, once I can get it over, for some reason my touchpad is not cooperating. Can we move it over here? Control up. Doesn't work either. Great, okay. Oh boy. Alright, let's just do it in a window. It's gonna be easy enough, isn't it? Yeah, okay, we'll deal with that. Crikey. Alright, let's just use this. Right, so yes, this is right. That did literally happen. Okay, oh that's really good. I think we can deal with this. No, hold on, this is wrong. Let me try again. So we'll get there. Is that? No, that's wrong. Alright. Yeah, so I should have got a better setup. Let's see.
Click on the window.
No, that's okay. Well, given that we're pressed for time, I think I'm going to move on from this anyway. So, apologies everyone, like the technical difficulties and all that. We did look at it in a previous session, so if you are interested, then go back a couple of lessons. It is on YouTube anyway. So, with that in mind, implementation hiding. And a great quote again, all problems in computer science can be solved by another level of indirection. So we're going to talk about the pimple idiom. Sounds wonderful, doesn't it? Pimple. Pointer to implementation. So, let me close it. Right, so when writing a class implementation, sometimes we want to, hide our implementation from other people who are going to use it. So, we might be developing a library, right, which might be proprietary code, or it might just have so much code in it that I want to be free to change that code without everybody else having to recompile their application. And so the pimple idiom allows me to do that. So there's a few different motivations as a result, right? It could be security, the classic code. Okay, yes, that's kind of security by obscurity, but fine. Legal reasons, right? Maybe you just can't give them the source code. But again, maintainability, this is the best one. It allows you to create a boundary between your code and their code, and you can then freely make improvements and add updates to your codes, your implementation, without them having to recompile all their stuff just because you change the layout of your class or something. And as I put here, a typical use case is allowing you to. Oh, I don't have a laser pointer. One sec. Did that work? No, that didn't work. Let's just try this. Hold on. Oh, I see what's wrong. Where is it going? Cool. Okay, that should fix it. Back one. Is it alive? Okay, there we go. So let's turn the laser on again. Is that doing it? We've achieved a pen. Let's try and make that better. Yeah, there we go. Right. So yeah, one simple case here is allowing you to change the implementation and rebuild it without everyone else having to rebuild all their stuff because your implementation expanded or added some internal functions. So the way in which we do this is you create an outer class, a wrapper for your implementation. Right, that's why it's called a pimple idiom. It's pointer to implementation, and the wrapper class has the pointer to the implementation. So consequently, users of, I say our code, us as the developer doing this pimple idiom, the people using this wrapper only the header for the wrapper. They don't need to see anything about the implementation at all, which means we're then free to change that, right? Because they don't need to rely on it. So here is how you develop a wrapper. So we've got this imaginary implementation class, which I've called widget impl, right? And the first thing we need to do is forward declare it. So this is declaring that there does exist an implementation. I'm not telling you anything about its size, its members. You just know that it exists at that time, right? And this header I can freely share with any third party I like, because all they know is that I do have a class widget. They need to know about the wrapper. This is the wrapper class. So it keeps you a unique pointer. Again, this is the pointer part, right? Pointer to implementation. To the widget impl, the implementation. And then the second important part is that I have a default constructor. Again, that's a choice. You don't have to do this, but just to keep it simple, default constructor. I have a copy constructor, so they can copy the object, and a copy assignment operator, and of course a destructor. And the key point to note here is that all of these 4 functions, well, and the member function here called render widget, all of these are only a declaration. They do not have a definition. They must not have a definition. In order for this idiom to work, it must be the definitions must be separate, because obviously you compile the definitions, right? You build your DLL out of them, your library, right? Your executable code. This part on the right, this is all the executable stuff. So consequently, they shouldn't be seeing it, because then their compiler will try to compile that for them, when what you really want to do is to just run your code that you pre-compiled. So you keep them separate as a result. So on that note, in our CPP file, obviously first of all we're going to include our imaginary widget implementation class. So this header obviously is it's not in the slide, but essentially imagine this contains all the details of the class, which is private to us, private to our library. Nobody sees that. They only see this widget.h, right? This public header. This is the private header. So first of all, we have our default constructor. We have our initialize list, and we just use std make unique to construct the instance of the actual class. And this all works fine, because obviously if you don't know the size of an object, because this is just a pointer to the object in here, a unique pointer in this case, somebody can compile this just fine without knowing anything about the size of the object. But in here, this is making the real application. This is going to be in our pre-compiled code, right? Code that we generated and they simply call it. We then have a copy constructor. So, I just put it there for flavour really. It's not part of this concept. I'm just demonstrating how you would do it really, which is that you would call make unique, and then the constructor of widget impl will be called with a reference to the existing instance of the other widget class. Right? Make sense? A bit more. I mean, I actually, so I'll mention this later as well, but I will say this is not particularly important concepts now. This is again one of those cases where you may not know how to build an aeroplane, but at least you can spot that it's an aeroplane. So again, we have an assignment operator. It's just copy assignment, fairly simple. And then finally, the member function. This is also important to note. Obviously, because the implementation has a render widget function, you have to do a bit of boilerplate. It's a bit annoying. Because the implementation has it, you need to write it again in the wrapper and expose it in the wrapper. And then finally, for the destructor, we just default it. But the reason we keep it separate and put it here is because this results in the compiler generating code for the destructor. As far as somebody using our library knows, we have some kind of destructor. But when their compiler is using our code, it will just generate a jump, a call. It will call the implementation that our compiler generates. So our compiler will generate this here, and they will have to call it. So if you were to put it over here, it would have a completely different meaning. It would mean that they are allowed to generate their own destructor, which of course they can't do, because they don't know anything about this type. They can't destroy it. We can, because we know about it. When all they have to access is this full declaration, they can't actually destroy it. So consequently, it's important that the destructor is defined in here, as with everything else. You should define everything else separately from the header. It's a C++ 14 function. It's just a convenience for initializing a unique pointer. You could just use new if you wanted, but it's better not to. So, key requirements. In order to use this pimped idiom, you must ensure that all of your class member function definitions are separated from the header. Don't put any definitions in the header. And again, don't really worry about implementing these concepts. It's not that common in open source, which is probably what you're going to deal with or work with first. It is more common in business applications, large code bases especially, because it means that one team can use this idiom, they can mess around with their implementation, ship a new DLL, and then the other team don't have to rebuild anything, just drop it in the folder and run the program.
There's one instance, for instance, where you would have to define a function in the
Template. That's one. Yeah, also inline functions. Well, actually, no, that's not entirely true. Tristan, you can declare a function. You can use the inline keyword on a function, can't you? And not include a definition. Oh, you have to include a definition. So I thought it specified linkage, and I'm not sure. If I just stick the word inline in front of a function, I just specify linkage, it doesn't mean that I must put a definition in the header. It does. Fine. Okay, it does. Or I guess you get a linker then if you don't. I'm still not. Yeah, you get a linker. Okay, yeah, makes sense. So, could be which tells me. But no, templates would be no explanation, but putting everything in a header, yeah. But then if you were building a template function there, or template class, right? Sorry, that's wrong, sorry. Class template or function template. Obviously a template doesn't exist, right? It's like a cookie cutter, right? You don't eat a cookie cutter. You roll out a cookie dough, punch out a cookie that's cinnamon flavour, punch out another cookie that's vanilla flavour, right? The individual cookies that you punch out from the template, you instantiate types, those are usable.
It's like a preprocessor directive, isn't it?
It's not a preprocessor directive at all. It's part of the compile system. It gives you all the strong type stuff. Macros, preprocessor, they're all just simple text substitution. Templates are first class part of the language.
So this pimple is incompatible with the template.
Basically, yeah. It wouldn't really.
It's not a
make
piece
sense.
of drop-in code.
What do you mean?
You can't have a piece of drop-in code as a template because
Well, to your point, if I just jump back a second, strictly speaking, if you want to be a bit fancy and clever, you could probably get away with templating the wrap class so that you could reuse the wrap class for different implementations. You obviously couldn't template the implementation. Or at least you could inside your library, but you'd at least have to punch out some concrete version of it that you compile.
You're stuck using one type.
What do you mean?
We did input. That's the
Well, no, I mean not if this was templated, because you just have one import wrapper, and you punch out the template with widget import. You'd punch it out with another forward declare class.
You'd have a unique pointer T then.
Yeah, exactly.
Okay.
So yes, again, it's more common in large business code bases for performance reasons. Different teams can work on stuff separately and then just shove their compiled DLL in a folder and hopefully it works. Because it acts as this firewall between the changes you make to your stuff, your implementation, and whatever else everybody else is doing, right? They don't need to know now about what your implementation is or does. So we've only got 3 minutes left, unfortunately. But we did have an exercise which would take you through exceptions, or I would invite you to carry on working on your tic-tac-toe if you haven't done it already. But given that there's only 3 minutes left, well, yeah. So thanks a lot. Tom? Right, 1 second, folks. Sorry for the technical difficulties today. We are getting adjusted to our new and fancy equipment. If I can just find my mouse, because it's gone absolutely God knows where. Right. Okay, let me just hand over to Tom.
live?
You are.
Okay, thank you very much for Ollie, and again, happy birthday to the birthday boy. So, obviously, after we finish the class, I invite everybody to join us in a pub. So, where this guy's birthday as well, and look after Tristan and Ollie to make sure that they're happy and they'll come back next week. And just make sure that the place is spotless clean. So we are invited again for the next class. I hope to see you next week, and on those who come on Thursday, see you on Thursday.
Thanks very much.